Welcome. In this video, we're going to continue our discussion of solid-state physics, and we're going to focus our attention more on light. But before we get into that, let's review what we've done so far. From the discussion of solid-state physics, we were able to account for how metals bond, primarily understanding what kind of internal structure is for metals and what causes the metals to have certain electrical properties. And we were able to account for that using the band theory of metals. And the essence of this approach, of this understanding, is that atoms, we go from single atoms to molecules or crystals, that is, more complex structures, an ensemble of atoms. And when we go from from single atoms to an ensemble of them, certain things are going to be changed. So with singular atoms, we had discrete energy levels which were allowed for electrons to occupy. However, when we go to a collection of atoms which form a crystal, typically a crystalline metal, what happens is that these discrete energy levels are replaced with continuous bands of allowed energies. Hence the band theory of metals. Atoms at discrete energy levels, molecules or crystals have bands. And these bands are a very a stack of many discrete levels which are, for practical purposes, continuous. That is because you have many atoms in a crystal, on a crystalline metal. And this understanding of, or this transition from atomic to crystals or molecular structures allows us to understand the electrical properties of metals. That is, metals can conduct electricity based on what we call a conduction band. If there are electrons in a conduction band, then that molecule or that crystal will have very good electric properties. So those are the major takeaways of the band theory of metals, is that we go from single atoms to an ensemble of them, which are typically crystalline. That is, they have a regular structure. And in this kind of a transition from atoms to molecules or crystals, the singular energy levels, which we saw in Bohr's model of the atom, become bands of allowed energies. And depending on what bands are occupied, in particular, depending on the conduction band, the metal will have certain electrical properties. So beyond that, we went further to account for semiconductors. Semiconductors are metals which have properties that display insulator behavior, and when the conditions are appropriate, they will then behave as though they were a conductor. So they are kind of a hybrid. They both act as an insulator and as a conductor. And these semiconductors are produced from crystalline metals. So here you could include that specifically these are typically crystalline metals. That is, they have a regular structure which has typically a crystal-like. Okay, and the key here is that semiconductors have a completely filled valence band. Their valence band is completely filled. Moreover, their conduction band is empty. That is, there are no electrons in a conduction band. If there were electrons in a conduction band, then they would be conductors. But typically, your semiconductors will have an empty conduction band, and they will have a small band gap. Band gap is the region that is forbidden, is the region between allowed energy bands And here in the picture we have signified it with EG. So this region here is a valence band, that region there is the conduction band, and this part is the forbidden region. If this region is very large, then the metal, which has a large band gap, will have insulator properties. If the band gap is very small, if the band gap is very large with the conduction band being empty, then that metal is going to be insulator. It's going to have more insulative properties. However, if the band gap is small, that means, band gap small and conduction band empty, that means we don't need a lot of energy to get electrons from the valence band over to the conduction band. And that's exactly what a semiconductor behaves like. It's when the conditions are one way, there won't be any electrons in a conduction band, but let's say, for instance, as you heat it up, you supply energy, then there'll be enough energy for these electrons in the valence band to make the jump to the conduction band, and therefore then this metal will behave as a conductor. So that's how semiconductors those are semiconductors. Typically they will have a small band gap. And the way they are produced in practice, semiconductors, in particular the way this band gap is typically made small, it is by the process of doping. And doping is simply the addition of an impurity. So you may have a metal which is made out of some pure substance, let's say silicon. And silicon, based on our previous discussion, typically it looks like it shouldn't be a good conductor because its valence band is completely full and its conduction band is empty. But when you introduce an impurity, silicon becomes a very good conductor because some of the electrons, depending on what kind of impurity you introduce, you would either have electrons here or you'd have holes here. Because of this, the impurity that we introduce is also known as an activator. So it's the element or the atom that causes this metal to suddenly have conductor properties. So by adding small concentrations of impurities to pure metals, we can make it to behave as a semiconductor. Okay, what kind of semiconductors are there? Well, we saw that there was an N-type semiconductor, and here the impurity introduced caused the metal to have extra electrons available in the conduction band. And you might look at this structure as an example. These blue or teal spheres, they are representative of a silicon atom. And when we supply to the silicon atom, we remove a silicon atom, we replace it with an arsenic atom. Because of the way our arsenic has, or the number of electrons has in its valence band, arsenic will have an extra electron, which means in this site, there will not be 4 electrons, but there will be 5, which means this crystal here would have a filled valence band, but then 1 electron would need to go to the conduction band. This extra electron would need to go to the valence band. Will need to go to the conduction band. Conduction band. This extra electron would need to go to the conduction band. And because it's in a conduction band, it's available to conduct electricity. And because this is an electron, the particle that's available to conduct electricity is an electron, hence it's a negative charge carrier. This type of a semiconductor is referred to as N-type. N refers to negative. that is the guy responsible for transmitting or conducting electricity, is a negatively charged particle, which in our case it's an electron. The other kind of semiconductor we saw was the p-type. And P here refers to positive. And although positive doesn't mean in this case a positive charge, but it means a positive overall charge. It doesn't mean a positive particle, but it means a vacancy, a shortage of electrons. This happens, for instance, when you take silicone, a crystal of silicone, and in one of the sites you replace it with, you replace one of the sites with, for instance, a boron atom, and a boron atom has 3 valence electrons, which means that one of the sites there's going to be a shortage of electrons, or a vacancy, an electron vacancy. Because this was supposed to be filled with an electron, as a result, this site is going to have a net positive charge. And that charge is what we mean by P here. This hole, this vacancy, is what we call a hole. This vacancy here, we call it a hole, and it has a positive charge, or it lacks electrons. Now, because we have a shortage of electrons here, when electrons move to fill this gap, they're going to create a hole. They will leave a hole behind. So actually, as electrons move in to fill in the hole, you would see when the electron moves to the left, the hole is going to end up on the right. So here we can say that the charge carrier is by the movement of the hole. It's the hole that's propagating to the right in this particular example I just made. So hence, in this particular type of semiconductor, the charge, or the type of quote-quote particle that's responsible for propagating current, is the P is a positive charge, which is why we call this semiconductor p-type. Okay, it turns out that not only does the band theory of metal account for how our substances behave electrically, but also it's responsible for accounting for how metals respond when they have energy. Most metals, as we know, when you warm up something, when something receives a lot of energy, it would typically be put into an excited state. And because this excited state is unstable, eventually it would de-excite and eject or emit the extra energy. But we know that different metals emit differently. Their way of emission, the way of getting rid of the excess energy by emission, is very different. And this can be understood from the perspective of the band theory of metals. And one of the very interesting things in radiography is luminescence. That is the emission of light without high temperatures. We know that whenever you increase the temperature of a substance, it will warm up, eventually it will glow and produce some kind of a light. However, in certain metals, we do see this kind of light being produced without the need of raising the temperature to high levels. That is what we mean by luminescence. It's basically a cold light emission. So we're emitting light without the excessive temperatures. Luminescence is a general term overarching many types of cold light emission. The first one is fluorescence, which is very important in radiography. And the other one is phosphorescence. And the last one is thermoluminescence. We're going to talk about them, and we're going to understand these processes or these types of cold light emission from the perspective of the band theory of metals. Okay, so remember that semiconductors are produced by the doping process. That means we started off with pure metals and we introduced an impurity, and as a result of that, the metal, this doped semiconductor, took on certain properties. So the point is, a semiconductor will also have a conduction band, it will also have a valence band, and it will also have a band gap, the forbidden region, just like pure metals. But because of the doping, because of the introduction of this impurity, typically semiconductors have what we call a luminescent center. This is a region or a band of allowed energies, but these allowed energies, they are inside, they reside within the band gap. The band gap was completely forbidden when the metal was pure. But because of doping, that is this impurity, allowed certain energy levels to reside or to be introduced in the band gap. That's what's key here. The doping process has introduced allowed energy levels within the forbidden band gap of the pure metal. This region, when the metal was pure, could not be occupied. But now, because of doping, there's a region of this band gap which is now can now be home to electrons. That is very, very important. Okay, again, these energies would be absent in a pure metal, but they were introduced by the doping of that metal. We call these regions the luminescent centers. And moreover, electron traps are introduced whenever you dope a substance. The reason why there are electron traps is because when you are doping a metal, sometimes or many a time, the doping does not produce a perfect crystalline structure. For instance, over here, I use an example. You see, when we introduced this boron atom, the structure here was still maintained. But this is not always true. It may not be that one boron is surrounded by all silicon atoms. It could be that you have a boron atom here and another boron atom here. So the point is, the way of doping, or doping, is not always perfect. In real life, it is not always perfect. And because it's not always perfect, this kind of imperfection is going to cause allowed regions, I should say allowed levels. So luminescent centers are a energy band. Maybe let me make that clear, that this is a band. Whereas electron traps are just a level. It's just a singular level, almost like in the case of an atom. These electron traps also reside in the band gap, and the reason why they show up is because of the imperfection in the crystalline structure of a semiconductor once we dope it. Okay, so those are the two important things that doping introduces to pure metals. They introduce luminescent centers, which are allowed band gaps, or allowed gaps which reside in the band gap, which previously was forbidden, but now because of doping, there's an allowed region. And electron traps are also allowed energy levels which are in the band gap, and they are a result of imperfections in the crystalline structure. Now with that, we are ready to understand the different processes of luminescence. Okay, so here I have a diagram contrasting a metal, pure metal, with a doped one. And the point here is to demonstrate luminescence center diagrammatically. Consider this pure metal. We have a valence band. For now, we don't care about whether it's full or not. We just care that this is a valence band. And in this region, this is a forbidden region, that's the band gap. And then we have a conduction band, which is where free electrons are housed, and these electrons are responsible for the electrical properties of the metal. This would be a pure metal with no doping, no impurity. However, when we do introduce an impurity, that's what's on the right, as I've mentioned, that the impurity we introduce will allow certain energies, or will allow a region of allowed energies within the band gap of the pure metal. When we dope it, the structure, the band structure of the doped metal is going to look something like this. In between the allowed valence and the conduction, there would be an allowed region called a luminescence center. That is what we mean by a luminescence center, at least a diagrammatic look at it. Now, what about electron traps? Electron traps are not a band embedded within the band gap, but what they are just singular levels. And to signify that they are traps, I have drawn them here as though they were cups. In other words, electrons can reside here. And again, I would like to emphasize, they reside here. These levels, these energy levels, are possible but because of doping, which affects the crystalline structure. When we dope, the crystalline structure may not be perfect. And as a result, we're going to end up with these traps. This is a pure metal with a perfect crystalline structure, and here is a typical metal, a doped metal with an imperfect crystalline structure, or I would say, even if you like, you could say this is a theoretical and this is more of a practical. So theoretical on the left, and then this is more practical on the right, what you can actually make in the laboratory. Okay, now if we're comfortable with luminescence centers and electron traps, we are ready to talk about the different ways that metals respond to an energy stimulus. Okay, and this first process we're going to look at is fluorescence. And this is quite helpful to us because all the kinds of X-rays that we scan a patient, eventually we would like to see it. We want to be able to see it. We cannot use our naked eye to see X-rays, so eventually we gotta be able to look at the image and see it. And this process is heavily involved in that process of radiography or radiographic imaging. So in fluorescence, a metal which has been doped, that is, it has a luminescence center, when it receives energy, some electrons from the valence band will be excited to the conduction band. But remember, that energy caused the metal to be excited. As we know, in nature, excited states are not very stable. So the electrons would like to return back to their stable state. So eventually these electrons will make it back from the conduction band to the valence band. But remember now, our substance is no longer pure. It has been doped, and as a result, there is a luminescent center. So their way of going from the conduction band back to the valence band may be stepped. That is, the electrons may jump from the conduction band first to the luminescent center, And within the luminescent center, they might go from the upper part to the lower part. And in transitioning within the luminescence band, they actually will emit a visible photon. That is key. That is very important, is that on their way, as they descend from within the luminescent center, they will emit a visible light. And that's what we're looking for. This light is what we would like to detect, because this light will be proportional to the energy lost in going from here to here. And then obviously, once they get to this part of the the luminescent center, they will then descend back to the valence band. But the point is, this process, when electrons go from a valence band to the conduction, and from the conduction back to the valence, but through the luminescent center, this process is called fluorescence. Or this is what we use in fluoroscopy. Okay, we obtain visible light. I should mention this, that many a time, at least in radiography, the reason why an electron would move from the valence band to the conduction band, it's because the metal may have interacted with X-rays. These are the X-rays that issue from a patient. So when the X-rays that issue from a patient are excited to the conduction band, but then when they return back to the valence band, we're going to get some light. And this light is going to be proportional to the energy which was the incoming X-rays had. So we could use this light to build a picture of the anatomy we were studying. But the key important thing here is that we obtain visible light. That is very important. We started off with invisible X-rays, which motivated our electron from the valence band to the conduction, but we ended up with visible light. Okay, so that is fluorescence in the context of radiography. And then the other one is what happens when the electrons are not trapped, they go from the valence band to the conduction band, but not directly through the luminescent center. But suppose our substance has electron traps. I should say in the first example, I suppressed electron traps just for clarity, but in this case, I'm going to introduce them. Okay, so the same thing occurs in phosphorescence. This is the process where electrons again are excited from the valence band to the conduction band. However, on their way down to the conduction band, they don't go directly. However, instead of going directly to the valence band or directly to the luminescent center, they first land on an electron trap. And when electrons are in an electron trap, they cannot go from the trap directly to the valence band because of the trap. They first need to be released from the trap back to the conduction band and then allowed to descend out of the conduction band through the luminescent center all the way back to the valence band. So when electrons go through this detour of an electron trap, this is where we get phosphorescence. This type of light here will also be visible, but this detour, electrons that get a detour through electron traps, we call them they go through the process of phosphorescence. That's how they emit light. And by the way, I should mention, these types of metals don't even have to have phosphorus. Actually, phos is the Greek word for light. So it just means that they will produce visible light. The reason why we call this process phosphorescence has to do with the location of the electron trap. Notice here the electron trap is very close to the conduction band. Because it's very close to the conduction band, it's not so difficult for the electron to jump back into the conduction band. In other words, to move from the trap to the conduction band, you don't need a lot of energy to be supplied. Typically, the ambient temperature in which the metal is located is enough to get the electron to be released from the trap back to the conduction band and then through the luminescent center and eventually back to the down to the valence band. So because this electron trap is very close to the conduction band, this type of emission is known as phosphorescence. You don't need to supply any energy typically for the electron to be released here. It will automatically do so. Okay. Now the other one, the one I'm about to refer to, actually let's go to it. You will see that the electron trap is a lot further down. It's a lot closer to the valence band. So when electrons are excited from the valence to the conduction, and then they get trapped, it is not easy for them to jump from the trap back to the conduction. See how much energy needs to be supplied? Because of this, we need to supply some thermal energy. Hence, this way of emission is called thermoluminescence. The reason why we call it this is because when an electron is trapped on, well, when an electron is on the trap, we would need to supply energy. By heating up the metal, it would then begin to emit light. And the reason why it emits light is because when we heat it up, the electron returns back to the conduction band and eventually finds its path through the luminescent center and back down to the conduction band. So through the band theory of metals, we not only are able to account for electrical properties, but also the light emission properties of metals. The location of the luminescent center depends on the type of doping we have. The impurity we introduce would affect the size or would determine the size of the luminescent center and also its location, where it is. Although here I've drawn it as a short bar, a band here, but I should say that this band is as wide as the other ones. The reason why I put it here is just for pictorial purposes. Otherwise, the picture will be cluttered. But this band is as wide as all the other ones are. Okay. With this understanding, or rather through the band theory of gaps, we now can understand how light is emitted from different metals. Why are some metals more easy to emit light than others? It has to do with the kind of doping that has been introduced. So with that, I think we can pause here and I'll see you in the next one.